cover advanced topics, practical applications, and implementation techniques in quantum computing. Before moving on to the session, here is a short intro of today's guest. We are delighted to introduce Dr. Professor Noel Maria Deepak, who currently serves as an architect at Capgemini, a role he has held since April 2021. With over 18 years of experience in the IT industry, Noel brings extensive expertise in SAP technologies, specializing in SAP Commerce Cloud. Noel holds an impressive academic background with a PhD in computer science from Satyabama Institute of Science and Technology, Chennai. He holds a master's degree in computer application from Sri Ramakrishna Engineering College and a bachelor's degree in applied science computer technology from VLB Janakyamal College of Engineering and Technology. Professor Noel is highly skilled in various technical domains, particularly with SAP and related technologies. His proficiency in SAP HANA, SAP Commerce Cloud, SAP Hybrid E-commerce, Customer Data Cloud, and so far. Noel holds several prestigious certifications, including Project Management Professional, Agile with Atlancia Jira, and SAP Certified Application Associate. Throughout his career, Noel has led multiple teams on a variety of projects, demonstrating his dedication and technical acumen. His contributions include managing e-commerce implementation with a focus on design thinking and the user experience. Which is with such a honored professional, we are very much excited to have him today. I'm giving the session over to the today's guest.
Thank you, ma'am. And good morning to all. Today, we are going to see about the topic of leveraging quantum technologies for advancement in machine learning. So here, I hope you understand the topic well. So what we are going to learn for today. So let me explain this first before we jump into the topic. So I hope my screen is visible to everyone. I take this granted.
Yes, sir. Yes, sir.
Yeah. Thank you. Thank you. Thank you. So here, quantum technology. So quantum technology, in sense, we are moving into a step ahead in terms of computation using quantum mechanisms or quantum attributes or quantum technology. What we are going to use this quantum technology in the field of machine learning. That is the main topic of today's session. So today's session will be focused only on how we are going to use the quantum technology in terms of machine learning. So machine learning is, we know machine learning is already a giant with the specialization of AI and machine learning can do multiple things. In the machine learning, what we are going to do in terms of quantum. So that is what my approach of this session itself. And I have been developing projects on this quantum on the machine learning algorithms like person identification on a CCTV camera, real-time camera, and 24 hours camera. So in such an environment, how quantum is going to use for how quantum will be facilitate this kind of project. So that is what we are going to see today. So before we enter into the topic, just a brush up on quantum computing. So quantum computing, the concept of quantum computing was originally presented in 1982, way back by Richard Feynman, following the observation of exponential complexity involved in the modeling. So this is quite a complex kind of model. So way back in 1882 itself, people has started thinking about the quantum computing. So quantum computing is a revolutionary technology. When we consider this quantum technology, we have other paradigm shift of the classical computing. The classical computing is what we are using till today. Is the classical computing. So we are going to use something different from the classical computing. So unlike the classical computing, we are going to process the information in a different way that we adapt from the quantum physics. So the adaptation is the main key here. So in terms of the quantum mechanics or quantum physics, we have this the concept of quantum computation, qubits, superposition, and entanglement, and those other stuffs that we will be seeing in this session itself. So these kind of quantum technology or quantum mechanics or quantum principles that we are going to use in our project that what we used in a classical way of computing. So we are going to achieve the process that what we are not able to do with the classical computing. So that is the main thing. So before we enter into this kind of an approach, we'll see the basics of what is quantum computing and what are all the key principles will be applicable for machine learning. So in a classical computing, data storage and handling, we will be using the computation as bits. So we know we have zeros and ones, and the combination of zeros and ones will be taken up for the processing, and then everything in terms of zeros and ones we will be using. Whereas in terms of quantum computing, we have similar to classical computer, we have the quantum computers called quantum bit. We simply call it as qubit, and everybody knows the qubit. Qubit is a representation of the information. So we will be representing the information in qubits, so that we will be having a multi-dimensional or enlarged or more clear data can be exported. So that is what is required for machine learning. So this machine learning will have we have n-dimensional data, and handling the n-dimensional data in classical computers is we have achieved certain limit, but the training the data set, the processing the data, and handling the multi-dimensional data is still a challenge, and that too with the real-time 24 hours monitoring and 24 hours security. Those kind of data is really difficult to maintain, really difficult to process and analyze, identify a particular person or identify a particular sequence on the given CCTV camera footage. For example, whenever let's clear with the use case what we are going to discuss today. So there will be a CCTV camera, which is a prominent camera with multiple CCTV camera grid. So we will be having multiple CCTV camera grid. In sense, so we have a grid of CCTV cameras. In the grid of CCTV camera, the real-time vision will be captured, and everything will be stored in a central process with a separate data. So what this approach, what is required at this point of time is we need to identify a security threat, or for example, we think like a person entering into an office with a hazardous arms, like a gun or a knife or anything. Then this object needs to be identified, run real time. Real time, this object needs to be identified, and this object needs to be identified over the grid. So till now we have this data for one camera only. So in one camera perspective, we will see the data and we will analyze, and then we will do. But in a office, in a premises, if we have a grid of CCTV camera and a person enters into camera A, and when he goes through camera B, and we want to analyze this particular video sequence, then there comes a computational challenge. there comes a computational challenge. The computational challenge is here, it is a huge amount of data, and our real world computers, our real world machines, even the cloud or anything cannot be solved, but it will take more time. In span of this particular computational time, it may take 2 to 3 days to analyze that particular person has entered with the hazardous arm. Then it's no use. The person has already entered into the premise, and then he has already make the damage, and he has already damage has been done, and then we are doing the only the cleanup activity, or we are just doing the investigation activity. In case of we have a quantum computation available in this particular scenario, if we have the scenario in the quantum computation, this Qiskit has wavered that the fastest computer, which is taking 6 days of time, can be done in 30 minutes of time. It's kind of the comparison we have it with quantum computing and the classical computing. So in this scenario applied with this quantum, when we use quantum computing on this optimization of the machine learning algorithm, then the moment the person enters into the premises with a hazardous object, or any particular anomaly sequence, or any particular anomalies happen in the in this particular premises, we can immediately identify. So this is the kind of use case I am going to present to you. So how this is going to be happen with the terms of quantum computing. Obviously, I cannot show much on the project, or I cannot run the code for you, and then I can, but still I can give the low level design for this particular setup. We can discuss about the low level design for this particular project, and then we can obviously we can discuss about any other functionalities needs to be included, and everything can be discussed. Because this quantum computing, we know this is could be a clouds of cloud. We have a quantum thing available. I think we have some of the quantum machines available, like Qiskit we have, Qiskit and the bracket we have. So these kind of machines are available and delivered through us through cloud. You understood, right? So we have this quantum computing, which is having by the quantum service providers, and those quantum services are again provided to us in terms of cloud only. So we will be accessing the quantum resources over the cloud, and then we will be accessing our data and everything. We can be uploaded into the cloud to the quantum computational unit. We call it as a QCU. We when we call it CPU, we call it as a central processing unit, but here we call it as QCU, quantum computational unit. So this quantum computational unit will be processing our data through via cloud or particular thing. So before going to this detailed discussion about this one, we come to know what is a qubit. Qubit is an existence of state 0 and 1 or both. So we can say that qubit is it's neither 0 or nor 1. It is a both. It is available in the both the state, and qubit can be represented as bra and ket. So we call the bracket notation. We will call this bracket notation as 0 and 1, which means alpha square plus beta square equal to 1. So when we say like alpha and beta are the two computational units, and this will be represented as a complex number, and representing the probability ambiguity, amplitude of the given being this each state, the probability add up to mean to 1. So when we are into a probability, the total probability will be add up to 1, and we know that the gradient of the data. So in case of classical computing, either it is 0 or it is 1. we know that the famous prediction thing, right? We know we will be predicting our data through so through machine learning algorithm. So there will be a threshold value. For example, when I want to predict a particular data based upon the given output, like above the threshold value is the predicted data. For example, if a rain calculation I am doing above 7.8, I'm going to get the rain, and below 7.8, I'm not going to get the rain. So what will be the prediction will be having if we have the value of 7.5, and what the value of prediction will be we will be getting if it is like 7.8. So these are all minor difference, right? When we think about the huge amount of data, so in case of 7.5, it will be predicted as no rain, or it is a negative false prediction. And in case of 8.4, it will be a positive prediction. So the gradient of the data will be missed out. So when we say we are taking some decision based upon certain limits and certain threshold values, what we will do, we will take up this particular threshold thing, and below everything the threshold is going to be the negative value, the above the threshold value is going to be the positive value. So what to do, we using this, we cannot have a clear prediction. And if the data is like clear cut data, like zero, either it is zero or it is one, so this cannot be the case in the real world problem. So there will be again a gradient of data. So there is no called a good or a bad. So it's a mix of everything. That's what the world, and that's what every human is also. So we cannot take a threshold for his, and then above that and below that it cannot be taken. So this qubit is a very good example of qubit representation, stating that the data is represented at a mixture of both the cases, in a probability of the both the cases. So that is the qubit notation. In classical computing, if it is zero means zero and one means one. Here it is not like that. We will be having a combination of zero and one. That is what we have the qubit notation. So next comes the superposition. So here, whatever the value we are having is in classical computing, we take it as either a zero or either one. So it will be like a digital signature. The digital values only will be represent. In case of qubit, it will be available in a kind of an analog. We cannot say it is a pure analog, but still it's a kind of an analog. So we will be having the bra and kit notations are used. So next the main principles we use in quantum is the superposition. So superposition is a fundamental principle of quantum mechanics, and it is crucial to power of quantum computing. It allows quantum bit to exist in multiple states. So it is this superposition is the concept we adapt from the quantum mechanism to adapt the between the available of the data in two different states. It is simultaneously rather than being restricted to a single binary state, and it's caused with the classical computing. The key aspects of superpositions are, so the key aspects of the superpositions are, so mainly it allows the qubit to be in the state of both 0 and 1 at the same time, and opposed to be a classical bit that can be only be either 0 or 1. Mathematically, a qubit superposition is represented as a combination of two basics. So we got as two basics. One is a bra, and other one is a kit. And a general superposition state of a qubit is represented by the alpha and beta. So alpha of bra of 0 and beta of t. We call this as a psi notation, and then we can use this. The analogy, thinking of the superposition like spinning coin. While spinning the coin, it's neither a head nor a tail. So there should be an existence in a superposition. So in case of both the state, until it lands, we observe it is either it is a one or a zero. So we know that when we flip a coin, it is going to be either zero or one. But still, whenever the coin is not on the process of the flipping, during that particular time, what will be the uh, before the occurrence of the event and before the start of the event and the occurrence of the event. So in that particular time, how this particular data is available. So this is the data is growing. The person has entered into the camera and he is moving in this particular point, whether we cannot take a decision that he is a threat or not threat until until the mishabitance happens, until any thing happens. It is not taken as a pure true or false. So this is the main thing of superposition. Then impact on the combination superposition. So what will happen when we combine these two things, these two extremes? Superposition allows the quantum computers to process many possible states. So it can have many possible states, like from the zero to the most maximum, the integral values, the integral value or the differential values also we can be applicable. While classical computing would need to evaluate each possibility. So in case of if we want to do the classical computing, what we need to calculate these things slowly, one by one. Each every position of the data we need to calculate separately. We need to apply the function over the meaning of the over the integral values. The function goes 0 to 1 means the function f of x limit 0 to 1 means, so all the values the 0 to 1 we need to integrate it one by one, and then finally it needs to be integrated. Whereas in case of the quantum, it is directly we can get the value of the integral form. This is the impact of the on the computation. And why superposition matters in quantum computing? What is the main thing? Is a parallelism, efficiency, and quantum speed up. So this is the main concept of why we are going to the one key feature why we are going into quantum computing rather than the classical computing. What is more required is the parallelism. We are having the parallel processing without burdening the CPU. Without burdening, is the main thing is allows to handle multiple calculations at the same time. Even we can also do the in classical also we can do this ability is more without burdening the CPU, and the ability to explore multiple paths on the solution simultaneously. So we have an object at a particular position, let's say x in the space. It can be moving either of the in terms, if you want to predict a particular player's move. The for example, like you want to have an analysis of the game, so we can do the analysis of the game in the machine learning. So when we use quantum, it is like initially it will be very faster to get the analysis of the parallelism. What if the player would have been gone in the opposite direction? What if the player would have been gone in the 45-degree from this particular position to the opposite direction or towards the position? So these kind of calculations can be taken up on the runtime. And efficiency in algorithms, like we have many quantum algorithms, Grover, Shower, factorizing algorithm, and superposition enables which is enabling superpositions thing to test the multiple solutions at once, finding the answers faster than the classical computing. And quantum speed up, superposition combined with other quantum principles like entanglement and interface that we are going to see in the upcoming the over the period of the session. So with the given computers, this edge of the specific task is unsorted database, sorting on unsorted database, solving complex optimization problems, and simultaneously quantum systems. So this is the main use of this, the concept of superposition. So, any doubts? I think you can raise your hands and then you can ask. That either it is enabled or not, I'm not sure. But I am welcome for any doubts and then clarity every now and then, and that will be very good for us also to discuss the things. Okay. Next, I move to entanglement. So the this on like similar to superposition, entanglement is also a quantum mechanics principle that we adapt for quantum computing for our betterment. So what is the entanglement? So entanglement is a fundamental property in the quantum mechanics. So we should be clear enough what is quantum mechanics and what is quantum computing. Quantum mechanics is a, for my understanding, maybe it may be different also. For my understanding, quantum mechanism is a principle that has been designed, defined as a design, and the adaptation of the quantum principles into computing is called as the quantum computing. So that is the basic difference. And the property of the quantum mechanism that plays a crucial role in quantum computing, this entanglement, is this phenomenon where two or more qubits become interconnected. So when two or more qubits become interconnected, such as the state of one qubit is directly linked to the state of the another qubit. This here we have the interpolation of two particular data or two sets of data or two matrices of data or two set of n-dimensional data. So this one, we have this entanglement. Such an entanglement of one qubit is directly linked to the another data. So one data is directly linked to the another data. So we know like we have multiple data which is depending upon the other attributes. So attribute A will be depending upon attribute B. And we know like many data are depending upon the thing. So this entanglement speaks about the principles of having the data to be unique connection enables the some of the most powerful capability of quantum computing. And the key aspects of entanglement, as we said, when two qubits are entangled, entangled means tied up. When two are connected, entanglement, tied up or connected. When two qubits are entangled, the state of one qubit will instantly reflect the state of the other. So, of the total on average, it's interconnected, or total and the result is interconnected. Might not be the total and the variance will be interconnected, or it's like that. Whatever an attribute or a combination of attributes is interconnected to the third attribute, so that can be used. So that is what the we call it as an entanglement. Will instantly reflect the state of one state to another, even if they separated by vast distance. Okay. So even if it is separated in the vast time, so we know like this the principle when we enter into quantum itself, we will be learning this principle. When we have a particular atom, and that particular atom is divided into two, and one is kept in even if it is a different this distance, the spinning of the particular atom will be the same. If you change the direction of one particular object, then even it is a far away object will also change the thing. So this is the kind of entanglement. So this the value of one particular data will be different, will be interconnected with the value of another, and change to be the one qubit state will represent will result of the correlation change to the other without a physical connection or delay. So there might not be a physical connection, or I think whenever we do a particular operation in one particular thing, then the same thing will be happen to the other entangled data, and mathematically it is represented. So I'm just giving the mathematical part. So we'll just discuss about only the concepts and related to the machine learning only. And non-locality. Entanglement shows the form of spooky action at a distance, described by, we know that basic entanglement. This property does not transmit information faster than the speed of the light. So this is just a theoretical purpose. So it will be like one particular data. The moment you change the one particular attribute, the moment it will change the data in the, even if it is in any other location, it is highly connected and entangled. The attribute values. We as a machine learning perspective, or a deep learning or AI perspective, we will think about an attribute only. So a particular attribute will be entangled, and the moment you change the one attribute, the entangled attribute is going to be the change. So you will realize the change in the entangled the attribute. Okay. If you want more example or a local example also, you can just ask me. I can give more examples also. Considering the time, I'm just moving with the high level definitions only. And importance of tanglism is the parallel and the computational power. And entanglement enables the quantum computer to perform many calculations simultaneously, and exponentially increasing their computational power of the specific problems. When the computational power increase, we can able to have the entanglement data, and we can able to access those information. In the algorithm, like score algorithm or quantum error correction method, entanglement is the key. That is the key to achieve those. In our case, as a we want to understand in sense like attributes only. We'll take the example of attribute only. When such an attribute is going to be changed, the impact of that particular attribute is going to be changed in the other independent interdependent attributes. And we have quantum gates and quantum circuits. So quantum gates and quantum circuits, and it's a process of information is away the classical computer, and the use of entanglement qubit enables more complex and sophisticated operation. C naught gates, we have C gate, and we have a C naught gate. These gates are used for quantum. And using these gates, we will be accessing those informations, and compute those information, where the state of one qubit can control the state of the other qubit, another entangled qubit. When you say qubit, we can think about the information or the attribute. So one attribute is how we are going to change the attribute. The same thing we are going to modify the same thing. And quantum teleportation. So enablement of entanglement enables the quantum teleportation, a process by which the quantum state one bit can be transferred to another qubit at a distance without the physical moving of the bit. This is the basic mechanism. The communication is possible over this particular thing. And quantum teleportation doesn't transfer the information faster than light, but can be separately transmit the quantum information across the long distance, making it promise for secure communication. And mainly this quantum entanglement is the basics of the key distributions. So we know, like in cryptography we'll be having public key and the private key. And this key distribution protocol, the moment we change the public key, the private key is going to be changed. Those kind of things are the two parties share the same secure encryption key. The entanglement state are highly sensitive to any eavesdropping attempt, providing a fundamentally secure method of communication. And The sharing of public key and having a private key is going to be the usage of the moment we change the public key, the private key is going to be affected. At the moment we change the private key, the public key is going to be the change on the values. So entanglement in quantum algorithms, we have many algorithms on entanglement algorithms. So mainly we see Grover search algorithm. We have a Grover search algorithm uses entanglement to reduce the number of operations need to search. And on an unsorted database, achieving a quadratic speed up over the classical computing algorithm. It is mainly used for the search of the unsorted data or unstructured data. We can search the particular thing in the using the Grover's algorithm, and Shor's algorithm is used to for factorizing large integers, relies on entangled state to finding the periodicity in the function, which classical computer struggles with providing an exponential speed. And we have the third one is the quantum error correction. Quantum computers are prone to error, anyhow, with as per the thing. And entanglement enables quantum error correction code that protects the quantum information from decoherence and operational errors. Using entangled qubits, quantum error correction can be detected and correct the errors without directly measuring the quantum state. And the main challenges of this entanglement is deoccurrence and noise. Entanglement states are highly sensitive to interference from their environment, and small disturbance can called decoherence can distribute the entanglement state, leading to loss of information. Maintaining entanglement for a long period of time is challenging and requires careful, controlled environment. So when we have these attributes are interrelated, then we'll be end up in getting this information together. And having this correlation is a difficult and challenging task. And scalability, creating and maintaining entanglement state among the large number of qubits is technically challenging and costly. And achieving this large scale is a key area, and research is building practical quantum computers. Okay, so this is the main thing of the quantum computing. And next comes the interference. So we are moving to interference. So we understand the principles of superposition and the entanglement. Now we are having this interference. Interference is a fundamental concept in quantum mechanics. The functioning of quantum computing. In context of quantum computing, interference refers to the way the quantum state combines in a way it can be either enhanced or to cancel or certain probabilities. So how this particular entanglement data has been interfered, how we are interfering the data, how this particular data has been interference. So the moment we saw this in our progress report, the progress is marked as a red, amber, and green. So this kind of an interference we can be used. This property allows the quantum algorithm to amplify the probability of correct solution, and it can be used to identify the data and interfere the data accurately, and to come up with a given description. The key aspects of interference. Interference is a quantum mechanism. It's a phenomenon where probability, amplitude, and quantum states combine, which can either increase or decrease over the probability of the particular outcome. So the chance of increasing the probability or decreasing the probability, it's going to be a continuous value, not without the without the cutover value or the continuous values. By controlling the interference, quantum algorithms can guide a quantum system towards the desired outcome, maximizing the chance of obtaining the correct answer when it is measured. Constructive and destructive interference. Constructive interference is when probability amplitude of a certain quantum states combine in a way that increase the probability of a particular result. This is used in a quantum algorithms to amplify the likelihood of correct answers, likelihood of the correct answers. So how far it is it going to be the true. And destructive interference when the probability amplitude certain state they cancel each other. The values of the probability of those different attributes cancel each other and become to nullifying the reducing the probability of certain outcomes. This is useful for diminishing the chance of incorrect answers. So whenever we attempt a multiple choice questions, so what we will do, we will district the out of the context value. So out of the 4 values, what is the least most value is not applicable. When we order like that, and then we can come up with the correct value. So this is kind of an thing that's constructive and destructive interference. Amplitude and phase. Quantum states and describe a complex number called probability. The amplitude, the value of this particular thing is so both magnitude, the value of the bit, value of the data. The value of the data is which is the both magnitude and probability, and phase related to the angle or direction of the wave. So it has both probability and the magnitude and the direction. So the phase means the direction of the wave. The phase of each bit wave function, when considered as a wave function, determines how it will be interfere with the other state. Adjusting the phase allow quantum algorithms to manipulate the interference pattern, favoring certain computational paths and supervising the others. This is how the interference will work, the principles of interference. And the importance of interference in quantum computing is algorithm efficiency. So how we can turn this interference into our computational thing is the interference is the heart of many quantum algorithms, enabling them to perform faster and classical counterparts. So main thing is the main key selling point. USP is the computational fast and faster than the classical computing. When we use this thing, a constructive and destructive interference, quantum algorithms can sort, or certain problems with the more efficient. Groover algorithms use interference and amplify the probability of finding the correct answers in an unsorted database with a fewer steps of the classical search. Quantum speed interference allow the quantum computers to take the advantage of parallelism in quantum states and cancel out the incorrect solution, which can drastically reduce the operations and need to reach the correct solution. The Shor's algorithm of factorizing the large number interference is used to identify the pattern and the periodicities which classical computing struggle to detect the efficiency. So that is the power of this quantum speed up. Optimization of quantum states. Quantum algorithms often rely on multiple steps where interference is tuned and adjusted to steer the system towards the probable solution. This tuning done by the applying specific quantum gates. When I say gates, is quantum operations or quantum functions. You can consider you can think about the gates means like operations or the functions or the mainly the operations which modify the phase of the quantum amplitude of the quantum bits to set up the constructive and destructive interference. So these are the main quantum mechanism properties that we are going to use in our application of having the machine learning, quantum computing in machine learning. So main of the algorithms, as I told, is the Grover algorithm, QFT, quantum Fourier transform, and precise control are required and it can be used. Before we go into this the comparison of quantum and classic, I just want to ensure that everybody has understand the basic principles of quantum. This is a very basic principle of quantum, which we are going to use in our computational process, so that we can be implement our machine learning algorithm effectively. So this is the basic all four things. That's what I just want to ensure. I give a pass of 1 minute. If any questions, we can discuss, or we can move to the next session, the next part of the session in a minute.
Sir, very good afternoon, sir. Myself, Kanabadiram from Department of Computer Science. So I want to
Yes, sir.
know how does superposition and endangerments differ from classical computing, sir? Can you provide any real-world example or real scenario so that it will be easy for me to understand the difference?
Yes, sir. So let me come to the superposition itself. In case of in case of your prediction, in case of your prediction, if you take up the prediction, the gradient of the data, the gradient in sense, you will be having your the gradient of the data. It's not like either true or either false. In case of classical computing, we are taking is either true or either false. What about the intermediate values? What about the intermediate values? How we are not tackling them, right? So when we know, like in earlier days, converting the analog data to digital data, we will be having the loss of data, and converting back this to digital data to the analog data, we will be having this loss of information. So that is what we studied the earlier times when we are in DSP operations and everything. In this case, if you have your classical computing, the values are zeros and one means. What about the intermediate values? Either pass or fail. Then here, then what is the difference of a student getting just above the pass mark is considered as student getting 36 is also considered as pass, and then getting 34 is considered as fail. The difference between the two person is very less, right? How can we take a decision of this kind of a thing in a crucial real world data? For our studies it's okay, but still in case of real world data, how can you then we will be end up in getting this end up in getting into the wrong prediction. So the superposition, when we consider the superposition, no more we are having zeros and ones. We will be having the superposition data. So the mixture of 0 and 1. So that one, in case of our data, when we consider a huge amount of data, this data can be, it cannot be like a true pass or true fail data, or true negative or true positive data. There can be a mixture of this kind of both extremes. Both the extremes, a particular state of data can be a mixture of two particular extremes. That is how that particular data can be analyzed.
It's like confusion matrix. Am I right, sir? Actual value between the predicted value, true, positive,
Yes,
false, negative.
yes,
Yeah,
yes.
okay.
No, no. I'm talking about the outcome of the confidence matrix.
Okay,
When you
okay,
come
sir.
to this confidence matrix, you have predicted the thing, right? But still,
Yes.
the predicted value may go into the cat on the wall, right? It may go into that particular fall, or the example which I told you, 35 is your pass mark, 34 you're awarding the person as a fail, and 36 you are awarding the person as a pass. But the difference between these two things is the knowledge gained by these two persons is the same. Correct? So
Yes.
this in terms of the real world condition, we cannot take that particular thing. If we have a superposition data, if we consider the data as a superposition data, convert the data into superposition data, then we can have a better clarity of the data. And entanglement also, when we have one particular attribute, it's connected to another particular attribute. That's what I told, right? The qubits here in terms of quantum, it is talking about the qubits entanglement. But you think about the as a computer science background, you can think about the two different attributes. So the moment you change one particular attribute, your all the values is going to be changed. Consider you have your Excel sheet with all your calculations, and the moment you change one particular cell, the entire calculation is going to be changed, and then you will be getting different attributes. This can be also taken as an entanglement thing in terms of our attributes and everything.
Okay, sir. Thank you so much.
Yeah.
Sir, good morning, sir. Sir, good morning, sir. Sir, I'm audible, sir.
Yeah, you are audible.
Sir, I have a basic question, sir. Sir,
Yes,
you have the basic circuits, the gates, something like that, sir. Which
yes.
kind of role is suitable for this quantum computing, sir?
Which kind of role in sense the person who wants to enter into quantum computing, right?
So we have in the leading, we have three kind of OS. We have in currently Windows, Mac, and Linux. So
Yes.
coming to the quantum computing, which OS is better for that?
To answer it, like basically, it is not OS dependent and all. Basically, this is a concept of you will be having the quantum computing in different place, and then you'll be accessing through that thing, and then for you to use from your machine, you can use any of the your OS. Okay, similar to our cloud only. So if you are using your cloud, Linux, Mac, or even Windows, for cloud is going to be the same. So whenever you are your client machine, whatever the thing will be available, and you want to use it in the quantum, it's nothing. To answer your question directly, if you want to develop a particular circuit and you want to develop a quantum application, I would suggest Linux will be the good operating system to access this thing, and then you can design your circuit and then design your things, and then you can do it.
Okay, sir. I'm also have additional question, sir. So
Yeah.
which programming language also is better for quantum computing? Is there are new or existing ones?
The programming language here we use Qiskit and Bracket we will not say it's a different programming language. It's going to be an environment. So mainly like basic of computational is that is the main thing. Data structures and algorithm is what the mainly we want to be strong. And programming language in sense this can be implemented in any kind of programming language. It's again this everything is speak on towards the algorithm and other kind of the computationals only. So implementation that you can have it in any of your language, but bracket and bracket thing we can use this Amazon bracket. In AWS you have a thing called a bracket. You can use that particular service, and then you can code, and then you can see those kind of informations, information processing.
So okay, sir. Thank you so much, sir.
Thank you. Okay, we'll move to the quantum and classical computing. So what is difference between the quantum computing and the classical computing? How we are differentiating these particular two way of computational. Until now, we are using the classical computing, and here the basic unit is zeros and ones. In case of quantum computing, it is 0 and 1 with a superposition on both. It's a mix. I can say like a class, the basic term is a mixture of both. Zero, not either a zero, not nor a one. It is a superposition value. And in case of data processing, it's going to be a linear and sequential. So it is very easy to understand our programs and everything. It will be very easy to understand in terms of classical computing. Here the complexity increases. It's because it's a parallel and multiple state of simultaneously we are going to use. So it will be like a kind of a parallel computing, and we cannot have this attributes are in a sequence. We cannot take the attributes in a sequence, but these attributes are on a parallel manner. Parallelly, how these attributes are going to be affected, and rather the sequential parallel gives more efficient and accurate data. Superposition, it's not available in classical computing, but it enables allowing multiple state as per the qubit. Entanglement, it's both are independent bits. In the independent, when I say bit means independent attributes. So everything is going to be an independent attribute. But in case of qubits, it can be entangled and create a stronger correlation. Interference is not utilized in classical computing. Here it is a use of amplifying and correct the solution to reduce the incorrect ones. And computational power limited by binary operation. And here we have only binary operations, and, or, not, nor. So those are the limited operations. Yearly potentially speed up with a super specific speed up by specific problems. So we can have multiple operations can be implemented. Error rates, here it is low error rate, and here in quantum computing we'll be having high error rates, requires error correction. So hand in hand we'll be having error rates as well as the error correction. Application is general purpose of computing. So all are up to our web development, we can go for classical computing itself. So whatever the basic programming and web development, full stack development, everything we can do this classical computing. In case of quantum computing, given that quantum computers are not available to us ratherly, we are using to very minimal functionalities only, like cryptography and optimization. Optimization is it's a machine learning optimization and the simulation purpose only. We are going to use this particular thing, or augmented reality and machine learning, deep learning, cryptography. These are the only fields we are going to use this quantum computing, not for normal computational proper purpose, and those kind of things we are not going to use. And hardware, here we use transistors and then chips we use. Here we have a specialized hardware that is available in a particular by certain people, certain companies only. I don't know like how many uh, quantum computers are available. I think when I studied, like, I hear that only 50 computers are available or like that. Sometime back when I start studying about quantum computers, and I started at that time, I come to know that only 50 computers are available, quantum computers are available. That those things are leveraged through cloud. I'm not sure about now how many things are there. Maybe it may be increased. And development stage, it's maturely widely adapted. So it's already developed thing, and then we have multiple things are already used, and it is mature and then widely used. Widely used, that is a classical computing. And quantum is an experimental thing with limited commercial use. So it may come in next 5 to 10 years. We will be again learning in everywhere. We will be learning quantum and then quantum things. But as of now, it is it's not into a commercial use. Even multiple times, I was not able to connect until I get this Amazon bracket, and Qiskit also is there. But still, before getting these two things, we were studying everything on the theoretical part only. But now, before 6 months or 6 months to 1 year, we got this Amazon bracket. That is really very good thing where we can go and check all these things. That is really very good for using. Other than the Quizzkit, but still, Quizzkit also is freely available. But bracket is it's a some kind of paid version. It's for my particular opinion on the hardware part. And scalability. This is scalable, but approaching physical terms of thing. But theoretically, it is exponential scalability. We can say like it is scalable and everything, but challenge to achieve the quantum computing scalability, it's still in progress. We can say it's still in progress, so it will be coming in the near future. And problem solving, it is deterministic. We can solve the problem, we can achieve the solution. The solutions are already available, and it is deterministic and best for clearly defined solution. If the solution is clear, and then it is going to be the key. In case of quantum computing, it is probabilistic, ideal for complex and non-linear interactions like machine learning, optimization, and simulation and all. We cannot expect the particular object to behave on the given thing. It can behave on any particular time. So simulation and machine learning, and go on security purpose, we can mainly use this quantum computing. So I am mainly using in machine learning. So all my examples are coming like machine learning and only. Uh, it can be used in many other fields also. But still, my field of exploration is on machine learning, so I am sticking only to machine learning. But the application of quantum is rather less, mainly into many of the other fields also, like drug detection and other design and different part of the things are also, it has been used very well. So this is the basic difference between a classical computing and a quantum computing. Now we are entering into a field of machine learning. So we all know, we are all already everywhere we are hearing this word machine learning for past decade. At least for 10 years we are hearing this word, and even our students are creating projects using machine learning and deep learning and AI. And we also got many apps using machine learning and deep learning. And we are in an era of AI. So it's not a new term to us. We are already familiarized with the machine learning. It's a developing, the machine learning is nothing but developing an algorithm on a statistical model, and enables the computer to learn from the make prediction and decision based upon the data. So we have a trained data set, we have a test data set, and the new data is coming inside, and that can be classified into the main problem, the main applications of main machine learning is prediction, classification, and decision making. So those are the main things of machine learning. And this is in over time, as I expose the performance of machine learning is increasing on having the data, on having the digital data. Earlier we were not having much data in the network, but this is an era of data. We have enormous number of data. So this data can be manipulated. This data can be manipulated, and this data can be used anywhere. So that is the power of without the data, there is nothing called machine learning. Since we are having the data, we have this field of machine learning. So the analytics is the main purpose, and the computation is the main challenge for having such a huge amount of data. So the moment we enter into this data and then data manipulation, we will be having this problem of handling those data. The two, not a two-dimensional data or three-dimensional data. We are handling an n-dimensional data, tensors. We are not handling in no more matrix and everything, and we know like that tensors are available, and then we are handling a tensor of data, and that is also a multi-dimensional. We cannot even consider it as a 3 cross 3 or 3 cross 3 cross 3, or even it can be like n cross m cross l cross k cross h. It can be any dimension. So I did particularly putting a data on a particular space, on the n-dimensional space. It's unimaginable for us to visualize in the thing. So even we have come up with a thing of 3D data. We know 3D data. In the 3D space, we can identify a particular object in the 3D space. Now we are able to get the 3D images and 3D. Consider an n-dimensional data. How do you position this n-dimensional data? Based upon the attributes. The n-dimensional attributes, the attributes we are using. So here the quantum, how we are using this quantum. Before that, we'll see what are the main areas of machine learning that we need help of quantum. Okay, so I'm not telling this is applications of machine learning. We know applications of machine learning is we are using machine learning everywhere now. Even even for everything we are using machine learning and deep learning, where we are going to use. But where are the areas where the help of quantum will enhance the machine learning features? That is what here is a healthcare, disease prediction, and then medicine, medical image analysis, and then personalized medicine. So mainly this medicinal value is what we are going to be considered. I have an interesting example of a medicine prediction. A person who has this a disease on his child term, he has an allergic over the particular thing, and he has some disease in his early childhood days. Okay, that medicine that he took for that particular disease on his early childhood days is a contradictory medicine for that particular person after 40 years. This is a real-time case which has been identified by this machine learning algorithm. I think so. This particular person is coming to that particular disease, and then this particular is suggested by the when he admitted for some brain related disease, he was suggested by the medicine which is contradicting the medicine he took 40 years back. In this kind of data, this kind of analysis, this nobody can do except a machine. So this the data has been identified, and then the medicine has been clearly given to the person, which saves the life of that person until like if a normal procedure, like if a doctor analysis, okay, you have this symptoms and you go for this medicine without knowing the history of the particular person which he took 40 years back, the medicine he took, that is going to contradict this particular medicine that what doctor is going to prescribe now. And based upon the ethnicity, based upon the region, based upon the thing, we can predict even a personalized medicine. So now we are used to the Dolo 650 for all kind of fevers. Fever means we are putting Dolo 650 and then we are moving. We are not predicting anything. We are not having the personalized medicine. So this is a healthcare sector where we are to have a personalized medicine based upon our analysis and based upon our height, weight, my cholesterol level, my BP level, my blood rate, blood group, my ethnicity, my history of medicines, and then those kind of things. Everything is going to be taken care, and then the medicine is going to be personalized medicine. So here we may require quantum help to get into this kind of achievement on the field of healthcare and finance, fraud detection, algorithmic trading, and credit scoring. So now we have started using this fraud detection. So how to in our e-commerce field also we have implemented certain fraud detections has been implemented. Basically using the various attributes, not only the particular person's thing. When the person comes in, his age limit, his credit score, his locality, his friend's locality, and based on other things, everything has been calculated, and then this the fraud detection has been implemented. So one of the main thing which I have worked on is on this fraud detection is as you all know, I'm mostly into this e-commerce domain. So here, what is our problem is to get the acknowledgement. The country like European country and US, getting back the acknowledgement is a very tedious, a costly way to get back the acknowledgement. Whenever you see, like when the particular product has been delivered to 1,000 members, and getting the acknowledgement of this 1,000 members is going to be very costly, and you cannot claim that this particular person also. We all know, right? The Flipkart is sending stones instead of iPhone. So in that case, whom to believe? The Flipkart can also send to this particular iPhone only, but that the guy can tell, no, I got only a stone instead of the iPhone. So how to believe that person? So that is what the fraud detection. So based upon his data, the past data and everything, there not only that particular person's past data, it can be multiple attributes are there, and then it can be detected using the finance. So obviously, when huge amount of data is involving, you'll be having the huge amount of computation, and then we can have accurately. So once you when 1,000 orders has been dispatched, we can identify 10% as a fraud, and we can get only the 10% we can get the acknowledgement. And nobody say, no, I have not got your parcel. That cannot be done because it can be acknowledged. But rather the 9,999 people, it can be like we can believe that person. If they say no, it's not, means it's not. So this kind of the fraud detections can be done. And then algorithmic trading, based upon the multiple even trading in sense like multiple things, we can deposit in a lakh, and you can set an feature of like around 1,50,000, and then this trading will be happening, and then based on it will pick the stock, and then it will buy and then sell, and it will be intraday, and it will be given the duration of time. It will be make you the money of 1,50,000 on the given particular time. So that is what the algorithmic trading. I cannot, I just can include my bank account to the trading account and then the AI feature, and this can be done. So this is the field where we need AI and quantum is required. I'm not telling you this is where the machine learning is used. This is the field. Machine learning requires quantum thing. It can be enhanced more. And retail, product recommendation, customer segmentation, and then the inventory management, and manufacturing also, predictive maintenance, quality control, and supply chain optimization, and transportation, autonomous driving, and route optimization, and then the demand forecasting. So and NLP also, where quantum is required is language translation, sentimental analysis, and chatbots. So what is the way of the customer is talking, how he is talking. So those are things, and the computer vision. So there is object identification, and then the augmented reality. These are the main areas where machine learning is required. Quantum's expertise to solve these things. Initially, this quantum computing is in a machine learning. Quantum computing uses the quantum bits for parallel processing. Quantum machine learning algorithm Now we are entering into the how this machine learning algorithm is used in quantum. There's a quantum machine learning algorithm, QML. We know machine learning algorithm, we know all machine learning algorithm, we know. Then here we have multiple quantum machine learning algorithms are there. So the quantum computing uses qubits for parallel processing, and quantum machine learning combines the quantum computation with the classical computation. So initially it starts with the hybrid model, and quantum algorithm offers a potential speed up in optimization, scaling, and data processing. So this hybrid quantum classical algorithms use classical system alongside with the quantum circuits, SVM, QNN. We know CNN algorithm, we know RNN algorithms, we know neural networks. We know. Similarly, we have QNN. QNN is quantum neural networks. So those kind of algorithms is used for having the superposition data, and quantum computers handle specific part it is like not like entire machine learning algorithm is going. We are going to use the quantum. This particular machine learning algorithm, a particular part we can use the quantum computation, and then we can get the result. As a system that we use a function, right? Whenever we have a big system, we'll have a small module. Whenever we have a module, we'll have a small unit. And when in the small unit, we can have a small functional unit. That function can only be used in the quantum. It's not the entire application we are going to use in the quantum. So machine learning will be using classical computing as well as this quantum computing for a particular specific kernel of the kernel calculation, parameter tuning, and classical system manages optimization and model training. So it will be the mixture of hybrid quantum and classical algorithm. This is what is emerging now. This particular field is emerging. There's a hybrid quantum and classical computing algorithms. This is what we are thinking. And then quantum optimization for machine learning. Quantum approximate quantum algorithms for faster congruence, and a variational quantum eigensolver to solve the optimization problem efficiently. So mainly the optimization is the problem for us. So getting the optimal data, getting the data faster. That is what is the main thing. And then quantum enhanced sampling, the training the data set. So if we have some, whenever we want to download the Kegel data set, whatever might be the project, we go and we'll download the Kegel data set, and then we will develop our project over the Kegel data set, and then we will do it. That is not the real world application, right? That is not we are not going to get the data like that. The Kegel data set, it's a standard and clean data. That may not be our real world data. Our real world data will be dirty data, where it will not be it will not give you a clear picture. And then quantum enhanced sampling, that will be using for the efficient of sampling in the complex distribution, and accelerate the Bayesian interference, and then the generative models. So you can generate the Bayesian interference, and then faster exploration of the solution in space. Quantum data encoding technique, quantum feature map, and then embedding to the represent high dimensional data, maps, complex patterns. Even our map is going to be the real world map. Consider you see a particular map, whatever the map you are seeing as a Google map or something, that is going to be replaced in next 10 years as a live video camera. You go to a particular place, and if you want to see my particular place, it's going to be a live video camera. That's how we are going to see the person who are entering into the street. It's going to be a live video camera. That's how our map is going to be there. It's whenever you enter, you start your map, it's no more like a map like structure. It's going to be a real world data, and real time. That is not like a delayed data or something. The real world data is not that what we are going to be getting, and it is having to the encoding techniques, and useful of NLP, NLP now, the NLP how we are entering is when I'm really in a mood of my mood is very angry. I'm typing. I'm very frustrated and everything. I'm typing, but the NLP needs to understand, not only understand my knowledge, it also needs to understand my emotion. So the moment when I type hello, I have this problem in case of the customer care thing. Whenever I just enter my text, using the text, the NLP needs to not understand what I am telling. The NLP also requires to understand what is the emotion, how I am feeling. So that emotion needs to be transmitted to the machine to get the more appropriate data. And quantum clustering and dimensionality reduction. So we know like a dimensionality reduction. The K means clustering and then segmentation and PCA. We used to reduce the number of dimensions, right? We have some 50 dimensional data and we used to reduce to 5-dimensional data, and then we have the thing. So this entanglement and then the superposition will help us to have this dimensional reductionality very easier way. So if we have some 500 attributes, and but it can be come into a 5 attribute, and then you can consider only the 5 attribute having this impact of the 500 attributes onto you, onto the this machine learning algorithm. And quantum kernels of SVM, quantum kernels calculate similarity measures for SVM and enhance classification to performance of the complex tasks. And quantum simulators, optimizing quantum circuits for machine learning, and applications of quantum advantage. So these are the main area of this quantum machine learning algorithms. So this is how we will be using the quantum machine learning algorithms. Hope I clear what is quantum and what is quantum machine learning algorithms in terms of our field. And this is what I discussed. What is how the quantum machine learning algorithms are highly used in terms of this machine learning. So coming into the security, quantum computing security, I just given the use case. Before I go to the use case, we will discuss any questions we can take it up, or I can give my use case, and then how that can be implemented in quantum, that we can discuss. So let me take a 1 minute break only, then I'll be back on this use
Okay,
case
sir.
on
Okay. Okay.
smart AI surveillance. Yeah. I'm back. So here we are going to discuss about the optimized smart AI surveillance in quantum computing age. So the surveillance is a main thing. We need to have the surveillance. So we have the security, physical security was there, and then we have the CCTV camera. But CCTV camera is once the incident has been happened, then only we are going to see the CCTV camera, what happened, what needs to be done, who has done that, everything we will be doing after the CCTV camera is a recording feature only. But what if an AI system is embedded into the CCTV camera that can analyze the footage of the CCTV camera and identify a certain abnormal analytics. So everybody knows like the face detection and those kind of stuff is already there. We are putting our attendance based upon the face detection and those things are there. But here the AI needs to understand the particular sequence of this informations and then needs to analyze the situation of the particular CCTV camera. What if we have a grid of CCTV camera? Grid of CCTV camera is a, if I have an office and 360-degree under my office, if I have this thing, then it will be a 360-degree view for me. So if I have an office at my premises, I have put my CCTV camera. I have put my 4 CCTV camera. So each CCTV camera will cover 90-degree. So if I have this 90-degree view of my thing, and then when I connect this 4 CCTV camera, that is called as grid of CCTV camera. Grid. In that grid, when you combine these all this this video footage, combine all this video footage, and then imagine you are standing at the center of this particular grid, and then when you want to see the informations what has happened and that particular time combinedly, so you will be having a 360 view of the particular data. Hope I am clear. So it's not only the one camera's perspective, it's a perspective of the grid of camera. So a person is entering into this particular camera, gate A, what happened in the gate B? I want to analyze this. So a machine learning algorithm analyzing this particular thing. Here is the main approach. We are going to use the quantum mechanism to get the grid of data, and then how the gate A footage combined with gate B footage, and then combinedly how this is going to be happen. And then if a person entering into a gate A and he is like he may have 2 options. One is going to gate B or going to gate C. This is like if a person is coming up with a hazardous object or it's an anomaly is there, we can analyze that particular camera's option and then find out what will be the move. Where can I go and then catch that person? Can I go via gate B or gate C? I have 2 options, or I can go via gate D and then I can catch that person. So this kind of analysis on a real time data, having huge amount of data, and the really fast information is required. So this is where we require a quantum mechanism to feature this particular scenario. So with the advancement of digital world, crime investigation and then video surveillance become a smart way of using AI and IoT devices and technologies and security of sensitive information transfer between the IoT device. But the prime concern is the easy breaking of the classical approach. So here, when we use the classical approach or deep learning mechanism, it will be very difficult for us to manage those things. So here also we can use deep learning neural networks, ANN networks, artificial neural networks we can use, and then a simple neural network or a deep learning neural networks, VSAM, W4 and advisor. So these are all the classical approach. It can be used. This can be used. But think about if we have a in this kind of scenario, when we use this quantum cryptography, this part is the first. It will be using the face recognition deployed in the video surveillance. It helps to help the crime investigator to quick identification the high accuracy and precise location. And this particular can happen, and he can go and then find that person in a shortest path. How short he can reach the particular person. By speaking the quantum computers, we can have this kind of stuff in the exponentially less amount of time, and new quantum algorithms can do it, and more unique quantum data transmission, and then different systems being be sniffed or stolen, and it can be used. With the surge of demand of security and safety, the smart surveillance system has been acquired increased attention. So how we can use this kind of thing, and what are the algorithms already available? What are all the algorithms already available? And quantum cryptography for the data security. How we can use this for the data security. That is what our main purpose. And the mainly we use this quantum for the computational unit. The computational unit will be having, there's a high power of computation, will process the video and then the merge the video and then the 360-degree, and then find out the particular uh, person or anomaly we can able to. And the quantum machine learning algorithms often involves analysis of classification large number of vectors in a multidimensional space, in the trend of machine learning, and it's a big data. And quantum machine learning is going to be growing field, and we have many quantum algorithms, like we have quantum machine learning algorithms like supervised learning. We have QNN. QNN is similar to our RNN networks. We have QNN networks which uses the entangled or superposition data. The linear nature of the unitary input and output gates counterparts in the efficient QC machines in handling the linear input, and based upon the binary neurofuzzy network, it is tailored the binary membership of the function. Okay, and we have another algorithm called QRBNN algorithm. It's a quantum based on neural network. The main advantage of QRBNN algorithm is the ability to use the classical machine learning algorithm over the physical advantage of quantum based mechanism. So this is the main algorithm we are going to use. It's an RNN algorithm, but it is a Q based QRBNN algorithm. That where it use the both the functionalities of classical learning with the quantum based learning, and later it can be expanded to weightless neural networks. And we can have into the QCNN algorithm. And the QCNN algorithm that can be used in the order of log n complexity only, whereas the CNN algorithm, right, order of log power n complexity, which here we have order of log n only comparatively. And improvements in support vector machine and quadratic programming allows the applications algorithm to train the SVM. It's no longer possible in case of classical computing, but in QP algorithms, it's efficient training. So mainly this algorithm is used to train the data set and to have a highly efficient computations only. So this anonymous, like the anonymous data set, whatever the anonymous scenes that can be given as a thing, and then you can have a huge number of data with the hazardous weapons, and mainly this anonymity data, where a group of people entering into the thing with rushing people entering into this into the particular premises, gang of persons with mask entering into this premises. So those kind of things can be identified in the this surveillance and then security of the camera. And it can be also used in generative AI, where we can predict the sequence. So in case of a particular camera is there, and then it is covered 90-degree only, but remaining 360-degree, if I want to predict based upon the given person, the movement, I can predict the two different ways or three different ways I can predict, and then identify how the intruder could have been performed or could have been reacted in the situation. Okay, this is again a post-mortem activity only, but still this can visualize the thing. We have already seen this kind of thing as a theoretically. We have already seen this the scene in a movie, but still this will be of a particular person. If he enter into the thing, that the generative AI would be analysis and then tell how this person could have been moved. And this we can also follow the same thing, and then we can able to identify the um, hope you recognize what I am, which movie I'm telling. Okay. Okay. That's all about my session for today. So this is how we can leverage quantum computing into machine learning, and then we can use a particular thing in different use cases. I just explained one particular use case. Any doubts or clarification, I am open to answer. If no questions, I have saved you 20 minutes. So it's planned as 12:30.
Sir,
It's
2
still
minutes, sir.
12:30.
1 minute, sir.
Good afternoon, sir. Sir, good afternoon, sir.
Yes, ma'am. Yes.
Yeah, yes, sir. Kindly give about the quantum kernel, how differ from classical kernel in terms of efficiency, sir?
Yeah. So
Uh.
kernel, in sense, so we have a kernel. So we know like classical kernel is it's a processing unit, main processing unit on the this in case of classical computing.
Okay.
This
Okay.
this kernel, what it will do, it is the main part to do all your operations. This is a central unit for doing your operations. In case of your quantum kernel, this quantum kernel will be more efficient compared to the classical kernel, but onto the given superposition data. So if you use normal data for your this one, then I would suggest like go for the classical computing. Rather, if you want to use access your superposition data or high dimensional data, then this can be used in the quantum kernel.
Okay, so thank you, sir. Which algorithm is best for this classical kernel, sir? for
Classical
research,
kernel,
sir. Uh,
uh,
if
in terms
is
of
SVM is SVM support classical kernel, sir?
yes, it will support the classical kernel.
Okay.
We have the SVM which support for classical kernel also. But in terms of like SVM, when we use it in the quantum, it will be more efficient for us.
Okay, sir. Okay, thank you, sir.
Thank you.
Good afternoon, sir. I'm Professor Sonia. So my question is, sir, how quantum computing can be applied in the blockchain technologies?
Sorry, I'm not able to hear properly.
So
Is
can
it
you hear
about
me?
yeah?
Yes, sir. So my question is, how quantum computing can be applied in the blockchain technologies, sir?
Yes. So blockchain, as you know, blockchain is again a complex computational process. Using blockchain in sense, you will be using your data calculation. What kind of blockchain technology you are using?
The blockchain technology will be used to store the Bitcoin transactions. So we'll be using some online, uh, that is platforms to store all those transactions. We'll be having wallets also. Sir.
Yes.
So in that
So
case, how we calculate this quantum? Yeah. Sir.
So mainly, the blockchain is mainly used for the security. So whenever you use this quantum bitcoins, you cannot able to generate the bitcoin. The only thing is you can access the bitcoin, and then you can say the main purpose of this blockchain is to it has a high security. When you have the high security, you need a high computational and randomness of the enhanced security and quantum mining. If you want to mine your quantum thing, and then you want quantum encryption, and those are the areas where blockchain is used in the quantum. High potential of calculation, and then easier usage of the blockchain informations.
Okay, sir. Thank you, sir. Thank you.
Welcome.
Good afternoon, sir. Myself, Dr. Dhanush from Rathinam Arts College, sir.
Hi, sir.
Actually, I'm a chemistry faculty from our college, sir. So
Okay.
I have two basic doubts. So
Yes, sir.
in terms of chemistry, we use this perturbation theory to determine the quantum components of the modern things, sir. So
Oh.
how it can be replaced by the machine learning? Any modern techniques or modern tools are available, sir, to determine the perturbation
Yes.
theory?
Yes, sir. So actually, what I understood is you have a compound, and then you need to
Yeah. Yes, sir.
identify the compound the compounds factors.
Yeah. Yes,
The
sir.
factor which form this particular compound.
Yes, sir. Yes, sir.
For that. So that is the
Exactly,
basic
sir. Yes, sir.
idea. It is the
Yes, sir.
basic idea. So this one here, the quantum algorithm, how the machine learning algorithm can work is it can
Yes, sir.
have a multiple way of thinking of
Okay.
forming this particular compound. So when you have the history of your chemistry's observations and everything is
Okay, sir.
entangled in the data set, so it
Okay, sir.
can be like, for example, a component A is formed. Rather, this A can be what are the different ways this A can be formed. That is what
Okay,
machine
sir.
learning can predict and then identify the
Okay, sir.
root cause of the problem.
Okay, sir. Okay, sir. Fine, sir. Sir, I have another doubt, sir.
Yeah.
This quantum confinement. Can you explain this with the concept of machine learning, sir? Can we determine the quantum confinement using the machine learning techniques?
Quantum confinement.
Confinement, yes, sir. Quantum confinement is that for example, if you take a chemical compound, the proportion of each atoms present in the compound can be determined by
Ah,
the quantum confinement. So, is there any machine learning techniques to determine that quantum confinement, sir?
Yeah, we have the enhanced quantum future representation.
Okay, sir.
Future representation and
Okay, sir.
machine learning application.
Okay,
In
sir.
quantum machine learning, the
Yes,
feature
sir.
of the data set could potentially be represented by the discrete energy state
Okay,
and
sir.
allowing the encoding to the more complex information. So here, whenever we entering into the machine learning and then quantum is the, like we are entering into the world of high efficient data
Okay, sir.
and unimaginable data. So we have the way what we are going to think is going to be the n-dimensional
Yes, sir.
data. So it will be having the quantum confinement in the quantum kernel learning.
Okay, sir.
In that, you'll be having the quantum neural networks can also be used. Quantum neural
Okay.
networks can be used, and then energy efficient data encoding can be used,
Okay, sir.
and PCA, machine learning PCA algorithm can be used for the quantum confinement.
Okay, sir.
And maybe to the chemistry, whatever is the field of chemistry, the confinement can be used, and also simulation of the confinement. So what
Okay,
is
sir.
the simulation and what could have been done when we add this particular mixture without this, how could have been the result would be, that machine learning can predict with the help of your quantum.
Okay, sir. Okay, sir. Fine, sir. Thank you, sir. Thank you very much, sir.
Shall we conclude the session, sir?
Yeah, sure.
Okay. So, Kausalya ma'am will give you the vote of thanks.
Okay. Adanto.
Good afternoon, all. It's my privilege to propose vote of thanks on this 7-day online FTP program on quantum computing for next generation under DPT Star College scheme. I would like to thank CEO, Secretary, Principal, Vice Principal, Dean, Research and Development of Rathinam College of Arts and Science for their constant support to conduct this FTP. And I extend my thanks to Dr. S. Raja and Dr. T. Velumani, Head Department of Computer Science, and Ms. D. Uma Mageshwari, Head Department of Physics, for organizing this wonderful session. And I convey my sincere thanks to our today's resource person, Noel Maria Deepak, for advancing our knowledge and skills in this exciting field of quantum computing. Your expertise, clarity, and passion for this complex subject have truly inspired us, sir. Thank you. I would like to extend my thanks to our department faculty members and our committee for their immense effort. Last but not least, I would like to thank all the participants. With all your support, the second day of this FTP is completed in a successful way. Thank you all.
Thank you, ma'am. Sir, one more person asking a doubt. I think.
Yeah, sure.
Unmute your mic and ask a question, sir.
Sir, we know that in quantum computing, we can only observe a particular state after the measurement we do. So, how can we use superposition as a strength of quantum computing if we can only measure a one particular state out of all the superposition states?
So this superposition we want to understand in terms of the data. So this data cannot. I'm telling in terms of data. So this data cannot be either in extremes. So whenever you have a particular data which is coming to a prediction, we already trained the system, and the system is ready, and new available data is coming inside. That particular data is going to be classified into which part of this, which part you need to go. In this case, the superposition data will give us the clear cut idea. We'll have a clear cut idea stating that okay, this is the particular thing, and then we have the superposition information, and you need to be have this information to be which one. input data cannot be in the extremes. It can be in between the extreme, correct? So it cannot be go to the extreme. We cannot taken up with the given data. This data cannot be taken to the two different extremes. It can be either in one part or it can be into the in a mixture of both of them. So the supervision will help in that particular manner.
Okay, thank you, sir.
So, unmute your mic and ask a question.
Uh, um, Good morning, sir. Uh, Sir, am I audible?
Yeah.
Yes, sir, you are audible. Yes, yes.
So since we talked about the show's algorithm, which can potentially decrypt the modern encryption system, since we are using the factoring the large prime numbers, like, and we talked about the show's algorithm, which can potentially like easily factor out the primes. So it is led to the modern encryption system, like quantum computing.
So if I understood properly, you are asking about the encryption and decryption of the data, and you want to have this informations to be entangled, and it is main thing is the optimization is the main key for the quantum and the entanglement property. So your public key and private keys can be entangled, and then based upon the within a fraction of a second, whenever you have your change in public key and then private key, it can be accessible. Hope I have
So
answered.
is it like quantum computing comes into play in real world? We'll have to change our entire encryption system.
Yeah, in real world, you'll be having huge amount of data, right? Unimaginable kind of data. So that can be used.
Thank you, sir. So thank you for joining all of you. So today the session will be concluded. So thank you, sir. Thank you so much for
Yeah.
handling this session.
Thank you.
Thank you, sir. Sir, if it is possible, kindly share the PPT, sir. I will share to the other participants. Thank you, all of you. All of you completed today feedback. I will share it in the group and also in share it in the chat. Thank you.